All right, well, thank you again for the introduction. Hello, everyone. My name is Ryan Sochol, and I work in the advisement of Professor Liwei and Professor Luke Lee at the University of California, Berkeley. And so today, I'm going to be talking about a technique that we use to be able to achieve a high number of fluidic reactions on the surface of microbeads rapidly. And so first, I'm going to be talking about why we want to use microbeads in microfluidic systems. Then I'll be talking about why we want to achieve a high number of reactions on the surface of microbeads. And then the bulk of my presentation is going to be spent talking about our Micropost array railing concept and our recent results that we've achieved. So for chemicals and biological applications, there are essentially two main types of microarrays: static and dynamic microarrays. So static microarrays refer to systems where chemicals or biomolecules are immobilized onto a static substrate. And in contrast, dynamic microarrays refer to systems where those chemicals or biomolecules are actually immobilized onto mobile substrates. But between these two technologies, really dynamic microarrays present the superior technique. And this is due to a number of advantages, in particular, the enhanced reaction kinetics and the high surface to volume ratios associated with microbeads. However, one of the critical issues right now is that being able to rapidly achieve what we call multi-stage fluidic reactions, such as ELISA assays or other types of sandwich assays on the surface of microbeads, has remained a significant challenge. And so the motivation for this project is really to overcome that limitation and be able to achieve these rapid multi-stage fluidic reactions on microbead substrates. And the demonstrative example that I'll be talking about specifically today is the synthesis of what are called extended biological linkers on the surface of microbeads. So to give some background on extended biological linkers, previously, researchers have observed that when a fluorescent molecule is bound to a microbead, if the distance between the microbead and the fluorescent molecule is not large enough, then the fluorescence can actually be quenched. And so to overcome this issue, what you can do is you can add a biotin molecule first, and then another avidin molecule, and then this is what is called the extended biological linker. So afterwards, when a fluorescent molecule is bound to the microbead, due to the extended biological linker, which basically just acts as a spacer, the fluorescence response is enhanced. But the issue here is that being able to synthesize these extended biological linkers off-chip can be an extremely time-intensive and labor-intensive process. So to give you an idea of what I'm talking about, this is an overview of the synthesis process for extended biological linkers. So first, we begin by adding a suspension of streptavidin-coated microbeads. Then, we use a centrifuge in order to form a bead pellet. And this is done so that afterwards, we can remove all of the excess solution. Thereafter, we can add a solution of biotin, and during an incubation period, the biotin molecules can then bind to the surface of the microbeads via the biotin-streptavidin interaction. And so I'm not going to go into tremendous detail regarding the rest of this process, mainly because it's boring and a bit tedious. But the takeaway messages that I want you to have are, one, we're basically just repeating the same steps over and over and over again in order to immobilize additional biomolecules, such as avidin, onto the bead surface. And the second takeaway is that to do this entire process, which basically results in just 2 reaction steps, requires over an hour's worth of work and labor. And so this really is the goal of this project, is to overcome the time and labor associated with this process. And in particular, here we're trying to demonstrate a system to achieve a 9-stage reaction process on the surface of microbeads, and to do so in under 5 minutes. And to do this, we really need to turn to microfluidics. And so this is the concept that we came up with for our architecture. And the way that this works is that we have 2 parallel flow streams that are inputted into a microchannel, and these include distinct reagents. Additionally, we also have Micropost arrays, which are arrayed within the microchannel, and they're arrayed at an angle with respect to the fluid flow. And the way this works is that when microbeads enter the system, they are rapidly diverted into the adjacent parallel flow streams. And this can be done to rapidly wash the microbeads with additional fluidic washes or reagents as desired. So there are two main aspects to the design of this technique. And so the first aspect is determining what is the best angle to use to array the micropost at with respect to the direction of the fluid flow. And so the reason this is an issue is that if this angle is not optimized, then when microbeads enter the system, they actually begin immobilizing at the gaps between microposts. And this leads to a device failure. And so these are some of our experimental results of that. And so these are 15 micron in diameter microbeads. They're polystyrene microbeads, and they are immobilizing a system where the angle is 10 degrees. This is an angle of 5 degrees. And then even for an angle of 2.5 degrees, we still found that some of the microbeads would still immobilize in the gaps between microposts. However, even though some did immobilize, we did find that there were other microbeads that made it through the system without being immobilized. Nonetheless, however, for our final system, what we really wanted to have was a system where microbeads never immobilized within the system. And so, simply by shrinking this angle even further, specifically to 1 degree, which is not to scale, we were able to ensure that microbeads were never immobilized at the gaps between microposts. So the second aspect of our design is the overall architecture of the system. And so to go through this, first, we input a suspension of streptavidin-coated microbeads. Then, we input a solution of biotin molecules. We then have a wash solution. And the wash solution basically serves as a barrier between the biotin solution and the next avidin solution. Following that, we have another wash solution. And then finally, we have a solution of fluorescent molecules. So at the very end of the process, we can observe fluorescence on the surface of the microbeads. So this is an image of our actual device that we used to achieve these results. And so by using the micropost array railing method, we're able to ensure that the microbeads were mixed as desired with all of the different fluidic reagents and wash steps. And additionally, at the very end of the process, we used a previously presented technique known as micropost array trapping in order to immobilize all of the microbeads once the process was completed. And this was done specifically so we could then analyze the fluorescence at the end of the process. And so now I'm going to show you some of our experimental results. And so first, you're going to see microbeads being railed into the biotin solution. And next, these are microbeads being railed from the biotin solution and then to the wash solution. And then afterwards, these are microbeads that are being railed from the wash solution now to the avidin solution. And so by railing the microbeads into all these different solutions, we were able to add biotin molecules and avidin molecules layer by layer by layer. And so in our actual system, we repeated this area several times so that by the end of the process, we'd actually achieved a microbead with 4 biotin-avidin pairs bound to the surface of the microbead. And then following that, we mixed the microbead with the solution of fluorescent molecules in order to complete our 9 reaction steps. And at the end of the process, these are the microbeads that were immobilized under bright field. And then these are them under fluorescence. So one of the things that I did want to address today is that if any aspects of this presentation look somewhat familiar to you, it's possible that you might have read a recent paper that came out a few months ago in Lab on a Chip. And this is something that simply happens in research where you're working on something, you think you're the only one, and then across the world, this group's actually in Singapore, end up doing something that's very similar to your work. And it gets published in Lab on a Chip before you present at Transducers. So this happens, but I do want to talk about some of the differences between our work and their work. And so the first of which is that while their work was with microdroplets, obviously we worked with microbeads, and the physics there are somewhat different. But the more important aspect is in terms of scalability. And so, as you can see, the size of the droplet appears to be significantly larger than the size of the micropost. And this is different from our technique, where both the microbeads as well as the microposts were roughly the same size. And we feel that this lends our technique a little bit better to being scaled down to the nanoscale. So in terms of future work, what we're currently working on and actually finishing up is a multiplex platform for this, where we actually have 4 different bead sets, specifically one bead set that's divided into 4 different ones. And the way this works is that we add either 1, 2, 3, or 4 biotin-adenine pairs onto the surface of the microbead. And after mixing it with the fluorescence, we can then determine what is the optimal number of biotin-adenine pairs to bind to the surface of the bead to produce the best levels of fluorescence that we can see. So today we presented a simple, passive, yet powerful technique to achieve a high number of fluidic reactions on the surface of microbeads in a limited time. This is also the very first demonstration ever of railing microbeads in a microfluidic system. These are also the smallest microparticulates ever railed in microfluidics. And additionally, for solid microparticles, such as microstructures or microbeads, this is the very first 1D method, or a method that was created by a one-mass self-lithography process to rail microbeads. And so I want to thank everyone who played a role in putting this project together, as well as the presentation. And with that, I'd be glad to open up the floor for questions. Thank you.